Hey students, hope you did well on the exam, and I'm going to go through the solutions right now. I'd like you to self-grade it again, and after you self-grade it, hopefully it'll do two things. Give you an idea of what your score is, because it'll take me a while to grade all of these, and then also, answer any of the questions and fill in any of the missing pieces. So if there's anything you did wrong, maybe you could take this as a learning process. All right, so let's go through these 5 questions. Here's the first 4. Where's the fifth? The fifth one's on the next page here. But it says here a small cube of aluminum, and this is about the one we did in the lab, has a mass of 73.17 grams and a specific heat of 0.9. And watch the units here. The temperature of the aluminum is negative 200 degrees Celsius. 50 grams of water at 20 degrees Celsius is dripped onto the top of the aluminum block. The water cools to 0 degrees, and then some, that's going to be an important piece here, some freezes into a solid. And then there's 3 parts to this, and I do apologize, as I told you guys during the exam, that B and C should have warmed instead of cooled, since it was asking about the aluminum. And the aluminum's going to warm up, because aluminum starts really cold, negative 200, and then you put some water on it, and that eventually freezes, but not all of it freezes. And so I want to come back to that. Not all that freezes is a good point here, because what that would mean is we have a mixture then of ice and water. And that right there tells us that we've got to be at 0 degrees Celsius, at least in normal atmospheric conditions. And that's kind of what this is implying here. And it even says here, it also implies it again, how many grams of water freezes. So again, both of these are kind of saying that not all of it's going to freeze. Maybe 30 grams is going to freeze or something like that, or maybe almost all of it, 40 grams. I don't know. I really don't know how much freezes, but I am getting the distinction here as I read this for both these reasons, that not all of it is going to freeze. So hopefully A is some number between 0 and 50 grams. But it does tell me then what the final temperature is, and that's a big clue moving into the problem itself here. Now, you, I suppose, could even prove that to yourself, and maybe I will for this video, but during a test, I think you would be fine just to be able to start off and say, all right, number 1, the final temperature is 0 degrees Celsius. I mean, I think that's fair to do. However, if you want to kind of prove that to yourself, you may ask yourself something like this, that, okay, if the aluminum is going to warm up all the way from negative 200 all the way up to 0, how much energy would that be? And so the mass is the 73.17 grams. The specific heat is 0.9 joules for each gram, each degree Celsius. It warms up, and it's going to warm up 200 degrees Celsius. All right, so grabbing a calculator here, you would go 73.17. Multiply by 0.9, multiplying temperature increase of 200, and we're looking at about 13,171 joules to warm it up. Now let's talk about the water then cooling down and the water freezing. So if we look at the energy that would be then coming out of the water. The water would first have to cool down, and then it would have to freeze. Now, that's if all of it froze. And so these M's would be the same. That is, all of it cooled down and all of it froze. Of course, I'm under the impression just by reading this question that perhaps this M is not the same as this M being how much actually freezes, releasing its heat energy to warm up the aluminum. Maybe I should put aluminum here and H2O here. Okay. But I'm just going to give this a try to say, maybe this idea that all of it freezes and then it's going to get lower than 0 degrees. I mean, I still kind of want to answer that. And if I put in these numbers here, let's see, what was the mass of that water? 50 grams. So if I go 50 grams, and let me stick in the same units. The specific heat is 4.186. If you do it in joules, I know a lot of times we've done it in calories, but if you'll notice I did the aluminum in joules, so let me stick to that. And then times, now the amount that it cools down, maybe I'll put it as a negative 20 if it cools all the way down. And so remember then the negative being that the energy comes out. And so I guess I'd have to be a little careful here in my thinking process. As it freezes, as it freezes, I guess I would want a negative number. This is just how we calculate the absolute value of the heat during the latent heat of fusion. So I guess I would have another negative there. Okay, and then if it was all 50 grams, I'll put 50 times. And here's where the front page comes into play, or you could look it up for yourself. But there is a heat of fusion, and it is 333. Watch the unit. This is kilojoules per kilogram, but there's kilo on both top and bottom. So if we cancel that off, we would have joules per gram. And that would be good because I have the mass in grams, so I'd like it in joules. So I really want this number in joules per gram. And then fortunately, it's the same number because a kilojoule over a kilogram would be the same as a joule over a gram. They're each just have an extra 1,000 on top and bottom. Anyway, so it's 333. So 333, enter. All right, so the total of that would be then 20,836. And now that I think about it, I probably should have done this in their 2 steps, or at least this one, because I'm just noticing now that this is my proof then that it is not going to get lower than 0 degrees. Because it would take this much energy to eventually freeze all the ice and start to go lower. But we would only be having the 13,000 available as the aluminum is warming up. And so the warming up aluminum can only give it 13,000, and 13,000 is not nearly enough to cool it and to freeze it. But I probably should check to see if the 13,000 is enough to cool it down. So that's what this number is. And so that would be the 50 for the water, times the 4.186, times the negative 20. And so this is only 4,100, and 86. So yeah, clearly there is enough energy to bring the water down to 0 degrees. But then clearly there's not enough energy to freeze all of it. And so that is just confirming what I do know, and that is the final temperature is going to be 0 degrees, because then what's going to happen is this aluminum will have warmed up, releasing its 13,171 joules, and the first 4,186 cools the water down. And then the stuff or energy that still remains starts to freeze the water, but doesn't freeze all of it, because to freeze all of it, you would need 20,866. So good. The whole basic idea that some of it freezes is kind of confirmed here. All right, well, finally now I can actually then do this calculation, because then I would say something like this, the sum of all the Q's have to be 0, meaning the heat that comes out of the aluminum, so this is this calculation, the 13,171 joules that comes out of the aluminum, then goes into the, sorry, I guess I didn't say that. I said that backwards, sorry. The heat that comes out of the water as it cools, so they're negative. So the first negative 4,186 comes out of the water and then goes into the aluminum. So into the aluminum is positive. So as it goes into the aluminum starts to warm up. And I guess at this point we could take a moment to calculate, if you put in to the cold aluminum 4,186, you can see what the change in temperature is, and you would see it has warmed up a little bit. But I don't think that is worth our time. It would just tell us what the temperature is of the aluminum now that it's cooled the water down to 0, and now the water begins to freeze. Okay, but then this would be then the negative MLF, and it's these two together, this energy coming out of the water, that then goes into the aluminum. And the M here is really probably the hardest part of the problem, saying this is not the total 50 grams. This is the amount that actually freezes. As we did earlier, if all of it froze, we did a 50 up here, we would need this much energy coming out of the water and going into the aluminum. But we see we can't put that much into the aluminum. Otherwise, the aluminum, the aluminum only needs 13,000 to get up to 0. You put that much energy into it, the aluminum would end up being at a higher temperature than 0 degrees, whereas the ice then would all freeze and go lower than 0 degrees. And that doesn't even make sense. So we know it doesn't do that. So this is the number I'm looking for. And of course, remember, this is the 333 that we did a few moments ago here. All right, so let's see what we get. If you kind of imagine moving this to the other side, it's now positive. I'll just take this 13,171 and subtract off the 4,186. And again, if you pause for a moment and read this math again, here's what you're saying. You're saying here that we are going to then put this much energy into the aluminum total once it warms all the way up. The first little piece, this little piece, is the part that just cools down the water, so that it has nothing to do with how much actually freezes. Okay, so now once the water has reached 0 degrees, there's going to be put into the aluminum block another 8,985 joules of energy as the water begins to freeze. A fraction of the 50 grams freezes. So that's what this number must be equal to. So again, imagine that to the other side. So then if I divide that by the 333, I'm looking at about 27 grams. So the amount of water that freezes here is about 27 grams. All right, so that's probably the hardest part of this problem. There is some thermal expansion going on, and so if we come back to B here, it says, what is the volume of the aluminum cube after it has now warmed? And so the change in volume we learned was the beta times the initial volume times the change in temperature. And we also said then for solid objects, the beta is 3 times the linear expansion. So this is how much the volume is going to change. And in this case, it's a thermal expansion. It's going to grow. So I'll take the 3 and then multiply it by, and then here's where the front page comes into. Here are the coefficient of expansions. Of course, here's the alpha, so this is the linear expansion. Looking for aluminum, it looks like it's 23 times 10 to the minus 6. So 23 times 10 to the minus 6. That is in units of degree Celsius, or per degree Celsius. The original volume, well, we got to come over here to remember that it's a cube that's 3 with 1, 2, 3, 4 zeros. So it'd be 3 times 3 times 3. So 3 times 3 is 9, times another 3 makes 27. So this is a 27 and a bunch of zeros, cubic centimeters. And we are warming it up 200 degrees Celsius. So there is going to be a small increase, 3 times 23 times 10 to the negative 6 times 27 times 200. And we are going to increase by about 0.37. And I guess we do have a lot of significant figures here, so we could put 2, 6. Well, we only have 2 there, so maybe I'll just do 0.37. And I guess it depends what we mean here by significant figures, too. That's an infinite number of significant figures. But anyways, the new volume then, so the final volume now that it warms up, is the original 27 and then the 0.37 that it has increased as it has warmed and the molecules have bounced around a little bit more. Now the area, change in area, we had the same logic that you would have your initial area and your delta T, and you would increase it by, until we did these 2 dimensions, it would be 2 alpha. And so we get 1 alpha for every dimension. So if it was a linear expansion, in fact, that might be an easy way to do this problem, is just do the linear expansion, and then you can cube it to get the volume, and then you can square it to get the surface area. But I already went this far here. So this would be 2 times, and then this would be our 23 times 10 to the minus 6. The original area about 1 face, would be 3 by 3, so it would be 9 square centimeters. And again, we're warming it up to 100. So the increase in area would be 2 times 23 times 10 to the negative 6 times the original 9 times the warming up of 200 degrees, and at 2 decimal places it's 0.08, and so the new surface area would be the original 9 and then a hair more. And so there's the thermal expansion. All right, so a good problem, kind of a long problem, because it does require you to kind of see a lot of things here about the energy and the specific heat and the latent heat of fusion, figuring out the final temperature. I guess that's why it took me 18 and a half minutes so far just to kind of explain it. And as you know, you need about 25 minutes per problem during the exam. So we got this one in just in time. But hopefully, if you're not talking about it during an exam, it won't take you quite this long. And maybe, hopefully, the other ones won't be quite that long either. All right, let's move on then to the next problem. Problem number 2 says this. 1.35 moles of an unknown gas. So we don't know what kind of gas this is. It has a volume of 22 liters and a pressure of 150 kilopascals. The gas is quickly. That's going to be a key word. Because quickly, as we said, meant that it's probably adiabatic because we're not giving it time for thermal energy to come in and come out. So hopefully you caught that word. It's quickly compressed down to 10. So we're doing work on it. As the pressure increases to, and they give us another number. A, is the unknown gas a monatomic, a diatomic, and a polyatomic? And that one then is answered in the following way. We know that during the adiabatic process, this was our derivation, that the pressure multiplied by volume to a factor of gamma is some constant number. Meaning then if you took the initial pressure and the initial volume and raised it to a power of gamma, and then the final pressure and the final volume and raised it to a power of gamma, you would then be equal to the same thing. And so if you'll notice in this problem, they gave us 3 of those 4. They gave us 4 of the 5. They gave us the initial and final volumes, the initial and final pressures, but they didn't give us the gamma. And so we could solve this for gamma. And gamma then is going to tell us whether this is monoatomic or diatomic or polyatomic. So the initial pressure is this 150,000 pascals. The initial volume, I know gas has 22 liters raised to a power of gamma. It's then compressed to a final pressure of 558,093 pascals and a volume of 10, which will raise to a power of gamma. So now if we run through some math here, maybe I'll put the ones with raised to a gamma together, because a 22 divided by a 10 is 2.2, each raised to a power of gamma. And then if I maybe put the 558,093 and divide it by the 150,000, I will have over here 3.72. And of course, now if I take the log of both sides and do a log roll, I get gamma equals the log of 2.2 times the log of 3.72. And so I can get gamma by saying, okay, what is the log of this 3.72 divided by the log of 2.2? And so gamma is about 1.666. Now, if you remember, gamma is Cp over Cv. So if we look at our 3 options, monoatomic has 3 degrees of freedom. So that would be 3/2 R over 5/2 R, which is exactly what we need, coming out to be 1.66. So that tells me right away, without checking the other ones, that this is a monoatomic gas. The diatomic, by the way, would of course been 5 degrees of freedom. So I'd put 5/2 R down here and then add 1 R for Cp and molar specific heat at constant pressure, and I'd get 1.4. And I won't even mess with the polyatomic. We should probably keep going on here. But there's the answer to A. What type is it? And we get that from the adiabatic process and the gamma. So not a whole lot of mathematics work here, but knowing that you can decide what kind of gas it is from gamma, is really the big thing here. Now, part 2 of this says what? It says, how much work is done on the gas? All right, well, let me look at the first law of thermal dynamics here and point out here that in the adiabatic process, the Q is a 0. So perhaps the best thing to do for part B is to say that they're asking for work, which if you solved it with a direct integral of P dV is a little hard. But since the work is equal to the change of internal energy, and the internal energy is a state function, which we learned to be NCV delta T, and so it's probably worth saying it again. Notice this is the molar specific heat at constant volume. Even though this process is not a constant volume process, it's an adiabatic process, we can use it because this equation is a state function, and so it's valid for all cases, and we can easily prove that it's this for the constant volume But since it's a state function, it's also true for all the other processes. So this is how I'm going to attack this problem, is I'm going to then look at this idea. And so now, knowing that it's monoatomic and noting that I have 1.35 moles, I'll put in the 1.35, and then the CV would be 3/2 R for the 3 degrees of freedom. This is what we talked about back up here in A. And then I just have to do the change in temperature. Now, to get that change in temperature, maybe I need to remember that PV equals to nRT, or written another way, pressure times volume over nR is the temperature. Okay, so if I say, this is final temperature minus initial, why don't I try to say, well, what is the final temperature? And so I take the pressure, the volume, the number of moles in R, and then that would give me the final temperature. All right, so let's take it after the gas has squeezed, because they told me that final pressure as 558, 093. So that's it in pascals. Now the volume they said is in 10 liters, but to make this thing come out in units where I'm used to in joules, I need to convert that volume into cubic meters. So let me take the 10 liters and divide it by 1,000. The number of moles, 1.35, and the R in the units that I'm working with, which is joules and moles and Kelvin, would be 8.31. All right, so this would be a temperature of 497.5 after you compressed it. Now, before I compressed it, the pressure was 150, 123,000, and the volume was 22 liters. And again, let me convert that into cubic meters. Again, the number of moles, and again, the R. But this must have been the temperature before it was compressed, and it would be 294.2. All right, so now I can answer this question by subtracting the two. And so maybe I'll just come up here and grab that initial temperature and paste it, and subtract the other temperature, paste it, take the difference. All right, so the temperature difference is 203. Then if I go in kind of reverse order, times R, 8.31, times 3 over 2, okay, then times 1.35, I get a work, or a change of internal energy, of 3,421 joules. And so there's part B. Okay. Good. So that one wasn't nearly as long, but still a significant problem and a bit of a challenging of a problem one here. Let's look at number 3. Number 3 says we have 600 grams of a lump of copper that's cold at negative 100 degrees Celsius. It is placed in 70 grams of water at 10 degrees Celsius and 15-gram aluminum cup that is insulated from everything else. So right away I see this one is a lot like the lab, where I put a piece of metal into my calorimeter. My calorimeter has both water and the cup that is holding the water. Now, this is about the amount of water we did in the lab. The cup is a little lighter, and the water is a little colder than we did in the lab. And, of course, the aluminum we did, or the copper we did, was not quite this much, but we had warmed it, too, so we didn't cool it. Anyways, this is then what I would say is a good calculation here in the sense that we've got three objects to worry about. And an important one here is to realize that the water is inside the aluminum cup. Aluminum is a good conductor, and so just like we did in the lab, we've got to assume then, or we're able to assume, that the temperature of the water and the temperature of the aluminum cup would be one and the same because they're kind of fully in contact. And again, aluminum conducts really well, and we don't have much of it, so the aluminum is always going to end up being the same temperature as the water. It's certainly at equilibrium. So that's and of course, getting started, the cup and the aluminum are probably in equilibrium, and then after we stir it all up, the cup and aluminum and the copper are in equilibrium. Okay, so keep all that in mind. Now, the ultimate question is even harder though than like saying what's the final temperature. It says what is the change in entropy. So we've got a little bit of work to do here. But if you remember, the same thing we did back here on number 1, you are probably and hopefully beginning to see that there was so much energy needed to freeze water, and the water is not very warm. Well, probably what's going to happen here is the water is going to cool down to 0 and start to freeze, but probably not all of it freezing, because again, for all of it to freeze would take a lot of energy here, and that's what I'm getting at. Now, of course, not only does the water freeze, but also cool, but also the aluminum cools. So I, should be a little careful here. But I'm going to do kind of the same step, so it might take a little while here in number 3, like it did in number 1, to calculate this out here. And so maybe I will ask this question. What is it going to take, and how much energy is it going to take to warm the copper? Because again, I kind of suspect, because of this large latent heat of vapor fusion of the water, that if I just sat here and kind of speculated that I think this copper could warm all the way up to 0 degrees, bringing the water and the aluminum down to 0 degrees, and then things start to freeze, but everything's kind of locked in at 0 degrees. If I can do that, that can make this a lot easier calculation, because I know the final temperature of everything without maybe going through all the details of like how much water actually freezes. Oh, you know what? I think I'm going to even have to ask how much actually freezes here. Yeah. Okay. So it's going to be quite a bit of work, but let's just start working on that theory here. So I look at the copper, it's 600 grams. Now I need to look up that specific, here we go, the specific heat of my copper. Copper melting point, heat of fusion, down here, specific heats. Okay, so copper. Of course, here's calories. Let me do it in joules. And so copper, it looks like it has 386. Now, I suppose I should be careful because that's per kilogram. I want joules, but I want grams. Or I could change that to kilograms. But I already put 600 grams. So I'm going to go ahead and convert it into grams. And so that means I got to divide by 1,000. So this will be 0.386 joules per gram per each degree Celsius. Okay, so there is the specific heat of copper. And again, just asking myself, what if it warmed up the full 100 degrees and got to this magical temperature of 0 degrees? 600 times 0.386 times 100 would then be 23,160 joules. So that's how much energy would have to go into the copper to warm it up. Now, the other way around, the water cooling, the aluminum cooling, and then all of it freezing. Maybe I should do those, separately. I'll put it total here for a minute and then look at the two. But let's say the cooling effect. And so I'll do an MC delta T for the aluminum. I'll do an MC delta T for the water. And I suspect, just by looking at these numbers, that this amount of energy, because there's a lot of copper, and it's warming up a lot, this is going to be way more than is needed to cool down the water and the aluminum to 0 degrees. So it's going to at least cool down to 0 degrees. And then possibly all of the water freezing. But that's so much energy, probably not. But I need to check that here. But let's do the aluminum here. So we don't have much aluminum. Where'd the problem go? We only have 15 grams. So 15 times. And we need the specific heat of aluminum, which, if you went back to problem number 1, you'll see it was a 0.9. But just as well, we could look it up in that same chart we just did for the copper. There's the aluminum. Notice it says 900, but again, that's per kilogram. So divided by 1,000 is 0.9, okay. And this aluminum, we're going to cool down 10 degrees here for, or at least that's our question, cooling down from 10 degrees down to 0. So the change in temperature technically is a -10, if you will. So it comes out of it. And so this really is a small amount, negative 135 joules. So not much of a temperature change, not much mass, and not much of a specific heat. So very little energy. So you can see this energy that is coming out of the aluminum, that's going into the copper. This one here, going into the copper is a lot to warm up that copper. And some of that energy, but very little of it, is coming from the aluminum cooling down. That's just a small percentage. Now, for the water, it's going to be a much bigger number because we've got quite a bit more water than the aluminum. What was it again? 70 grams. So let me go 70. And then times the specific heat. That one you should probably know. Of course, that's 1 calorie, but it's 4.186 joules. Of course, you could also look it up here. I think they've got water in here somewhere right there. There it is. And divide by 1,000, so it's 4.187. Well, I got it as a 6. And again, it's cooling down by 10 degrees, so just a small amount. And so again, coming out of it would be 2,930.2, well, I'll just call it 30 joules. And again, hardly really anything coming out of it. So all the more reason for me to sit here and do this problem and say, oh yeah, this energy that has come out and cooled these down is small. These easily cool down to 0 degrees long before that energy goes in and warms up the copper to 0 degrees. All right, but now here's the big question. And what if, and I'll just say all 70 grams of water froze. Of course, releasing its energy and warming up the copper. How much energy would that be? Well, there's the 70 again. And, of course, the 333 that we did back in problem 1. Of course, we could look it up again here, but the heat of fusion for water, 333. Now again, it's got a kilo over a kilo, so I'll just cancel that. But this would be joules per gram. But this would be a lot of energy coming out as it freezes. This right here would require 23,310 joules to come out of the water as it freezes. And notice that would be way too much. If all of this came out, that would add up more than we can get from the copper as the copper warms up. So it's kind of be weird to say this, but if the aluminum and the copper cooled down and all the water froze, the total of all these energies would have to come out. That would have to go into the copper, and so the copper would warm up and be greater than 0 degrees. So all this would have to be 0 degrees or less, but this would have to be greater than 0 degrees. It doesn't make any sense. And in fact, I think this problem was probably set up so that if you just did this calculation and this calculation, you would realize right away, right from the very beginning, that it takes so much energy to freeze all the water that there's not enough energy in the warming piece of copper to do that. You can see already that that number there is bigger. Not by much, but bigger. And then you throw in those, it's very much bigger. And so you're going to say that, okay, not all of it froze. So this is a way of saying I definitely know for sure now that the final temperature is 0 degrees, and I also know that some fraction of the water froze, like in number 1. But even though I'm tempted to calculate how much water actually froze, let me stay away from that unless it's needed, especially during an exam. If this was a homework problem, I would definitely be curious, and I would do that calculation because I have the time. But during an exam, I would say, no, let's stick to the question at hand. So coming back to the question at hand, which it says, what is the total change in entropy? Then this is what the heart of the problem is. After the change in entropy would be each of the 3 items. And so let me just do copper first, and that would be an integral of the ds, which is the integral of the q over the t. And so if I think about the q for the warming copper, I could write it as mc dt over t, and then solve this by saying it's mc, and then I just have an integral of dt over t, which if I go from some initial to some final, would become the natural log of final over initial. Good. So the copper, I could actually get the change in entropy by just knowing what the initial and final temperatures are. So again, I know the final temperature is 0 degrees Celsius. Of course, this is not needs to be in Kelvin. So let me put in the mass. The mass is the 600 grams. Let's put in the specific heat of copper, as we said earlier, is 0.386 joules per gram. And we said for each change in Celsius, but it would also be for each change on the Kelvin scale. And then we would have Ln, and the final temperature. So the final temperature we just said would be 0 degrees Celsius. So let me put that as 273 Kelvin. And the initial would be, what was that initial? Oh yeah, it was a negative 100 degrees Celsius. So that would be 173 Kelvin. And so I can then get my calculator and get the change in entropy of the copper. So 273 divided by 173 for that ratio, natural log of that, and there's my logarithm. And then times 0.386. And then times 600, and I get about 105. I'll put 105.65. grams would cancel off, and this would be the appropriate units for entropy, which would be a joule per Kelvin. Okay. So there's the change in entropy of the copper. Why don't we do the change of entropy of the aluminum? And the aluminum is going to be kind of the same thought process, where I would have the MC delta T for the changing of the aluminum. So I'll just put MC dt over T, and when I actually do the integral, it's MC natural log of final temperature over initial temperature. And so now if I do this for the aluminum, I can put in the mass of the aluminum. That was the 15 grams. The specific heat for the aluminum, so kind of like this one, but it's a 0.9. Then the natural log of the final temperature. Well, again, we said it cooled down to 0 degrees Celsius, which is 273 Kelvin. But it started at a warmer temperature. I believe it was 10 degrees. Yeah, it started at 10 degrees Celsius. So that would be 283 on the Kelvin scale. So notice I'm taking the log of a fraction that is less than 1. So that's a negative number. And so sure enough, I get a negative 0.4, and I don't know how many decimals I should do. Maybe I'll just go 49. Now, by the way, I probably should have said something about the positive and the negative. See, the negative here means, of course, we are losing entropy. And that makes sense. We're cooling down the aluminum. The molecules are moving, or I guess I should say atoms of aluminum are moving a little slower. They're more organized. But up here, for the copper, it warmed up, so it was a positive. So one is increasing entropy and the other is decreasing. And in fact, the water is also decreasing. So maybe we should talk about the change in entropy then of the water. Now, the water is an interesting one because, and that's why I saved it last, because the water is coming into two pieces. The first part of it is a cooling down of the water. And so the way you calculate the change in energy is MC delta T when it changes its temperature. But the way you calculate the energy, and maybe I'll do it up here at the top of the page, when you're changing phase, the amount of energy is the amount of mass times the latent heat of fusion. Or put another way, a little bit of energy would correspond to a little bit of mass. So that's what I'm going to put down here, a dm L sub F over T. And so that would be my change in entropy here. Okay, so with that in mind, I would have two equations. I would have this MC natural log of final temperature over initial. And over here would be actually pretty easy because during the phase change, the temperature does not change at all. So this is LF over T times the amount of water that froze, which actually makes me kind of want to calculate how much water froze, but not really necessary because that right there is then the Q, the energy that went into it while it was freezing. Okay. All right, so with that in mind, let's put in our numbers here. So this first one, let's see, for the water was what? 70 grams of water. Just want to confirm that. Yeah, 70 grams of water. And the specific heat is 4.186 joules per gram for each Kelvin. And the final temperature would then be the 273 for the water, starting at 283. So that's a little decrease. And then this would just be the amount of heat, the Q, that went into the amount that froze. Let me hold off on that one. Let me go to the temperature. The temperature while it's freezing up is 273. Okay. Now, the reason I wanted to put the Q's up here is because, remember, I did some numbers involving energy earlier on, so to prove that it would be at 0 degrees, and now I'm going to take advantage of that. Because if you realize that the energy that is going to go into the copper that is using then to cool the water and aluminum and then also freeze some of it, the total we said was 23,160. Okay, so that's the amount that goes into the copper. Now, some of that energy comes from the cooling aluminum. So let me take away 135 from the cooling aluminum. And also some of that comes from the cooling water. So let me take away 2,930. All right, so this would say that by the time I cooled the aluminum and the water down to 0 degrees, the copper has warmed up to some temperature. I'm not even going to worry about what that temperature is, but to the point that it is no longer as cold as a negative 100, but it's still pretty cold. And the copper is still going to need another 20,095 joules in order to warm all the way up to 0 degrees. So that is the energy that must go into the water while it is freezing. See, that's why we said it wasn't quite enough to make all of it. This is the number we needed to make all of it freeze. And so it's going to be quite a bit, 20,000 out of 23,000. So it's probably somewhere in the neighborhood of 60 grams as I look at this number. I didn't actually calculate it, but I suppose I could have and then just used it right here, the 60 grams. But I'm just going to use the energy. And so this would be the 20,095 joules that is going into the ice here. And since it, coming out of the ice. So I need a negative here. And that's what I wanted to emphasize, that hey, we're organizing the ice. This should be a negative number. So cooling down, this is a negative number because the natural log is less than 1. So that's a negative number. But also this is a negative number. This is a negative number because right there, the energy comes out. So I need a negative. But it also then is organizing it. We're going from a liquid where the molecules are all kind of random and we're crystallizing it. All right, well, it looks like I need to go to a second page for this problem. Okay. And then I'll do the two calculations separately just to kind of see the two pieces. But this is a 70 times a 4.186 times a natural log of 273 over 283. And so there's a negative 10.5 joules per Kelvin. So again, a negative number, as again to be expected. It's organizing it. And the big one here is where most of the energy goes, the 20,095 divided by the 273, making a negative 73.6 joules Kelvin. Okay. All right. So finally, I can answer the total. This is quite a bit of a problem, at least long in terms of explaining. And what would be the total? So, coming back up here, the copper increases by 105.68. The cooling aluminum decreases some entropy by 0.49. The cooling water is about a 10.5. And then finally, the freezing of the water, going from a random liquid state into a crystal, lowering the entropy by 73.6, coming up with an overall change of entropy of 21, I'll just call it 0.1 joules per Kelvin for the total change of entropy. And I will point out that that was in alignment with the second law of thermodynamics, which simply says the change of entropy needs to be greater than 0, or equal to 0 for a reversible process, but greater than 0. And that's what we have. So we have something greater than 0. So we've got more randomness, more probability. That's why this happens. This is our discussion of what is driving the energy from the warm ones to the cold ones. And it's not some kind of force, it's a statistical probability. And this calculations give us that statistical probability. So I'm suspecting that might be the hardest one on the exam, partly because it has entropy, partly because it's long, and partly because we did the entropy just, 5 days before the exam. Or if you worked earlier, maybe you had it a week before the exam. But the entropy is just a hard one here. So I'm glad I took the time here to kind of work through, kind of a long work through, but totally worth it. And if I was taking the exam, of course I wouldn't be talking this much, but would be on a good pace, because now we're about 56, well, close to 57 minutes into the exam here. All right, let's go to number 4 and read it here. Number 4 here kind of shows a figure with a cylinder, tells us how many moles we have. Tells us we have nitrogen. That's good. Notice it's diatomic. Keep that in mind. I bet that's going to come into play. So we have a diatomic gas, and it's in a closed gas and closed by a movable piston. The cylinder is submerged in this boiling water. And I'm glad I explained to you the test that it doesn't start at the same as the boiling water, because it does say here, right, the piston is quickly pushed down from position 1, which has a volume of 33 liters, down to position 2, which has a volume of 6 liters, until it becomes the same temperature as the boiling water. So hopefully, like earlier on in the test, which one was quick compression, I guess it was number 2, that should be ringing bells in your head saying, oh, this doesn't have time for energy to change, flow in and out, so this is an adiabatic process. And if I put this in a PV diagram, so PV diagram, I guess I would be starting here with a large volume of 33 liters in units of liters, and compressing it down to 6, I guess I don't want to put liters there, 6 liters. Maybe it would be starting at a low pressure, but it would follow that adiabatic curve that looks like this. So if we call this A and then this B, this would be an A to B adiabatic compression from 33 liters to 6 liters. Now, they also said something really nice. This is how we know the temperature would be lower at A than the boiling one, because they said they squeeze it until it gets to the same as the boiling. So let me also just put right here in my chart, the temperature is 373 at point B here. Okay, so until it becomes the same temperature as the boiling water is how it's phrased. Okay, so then the piston is slowly expanded. Now in this one, hopefully the slow expansion tells you that it is then an isothermal process, because it would always be then at that same temperature. So normally when you kind of expand something quickly, it does work on the environment, so it loses temperature, it loses its energy. But if you do it slowly, it has time for energy from the outside to soak in, if you will, and it's coming from the boiling water. So this is an isotherm, and so if we call this point C, it would have a temperature, a temperature of 373 Kelvin also. And so I didn't draw a very good curve here, but I'm hoping you see that this is a hyperbola, whereas this is a power function. And so we said the adiabatic and the isothermic kind of have that same shape, but the adiabatic is steeper than the isothermic. Okay, but then it says it is cooled down at a fixed volume, so that's why I put C right over A, because now the pressure is being lowered and the temperature is being lowered. And they don't say what that temperature is. They just say it is lowered. It says the gas is then cooled at a fixed volume until the gas returns to its starting temperature. And then it asks us to fill in this chart. What is the heat, the work, and the change in internal energy of each of these three steps? Go ahead and fill in this table. All right, so maybe I'll just make this table here, and so we'll be talking from A to B, and then from B to C, and then C back to A. And I just noticed here that in the chart, doesn't really say which of these points is A, B, and C. So if you didn't call this A, B, C, that's fine. I just going to call them in the order that they labeled them. So I have a feeling most of you will, when I get down to start grading this, that you will have labeled them the same way. But if not, that's fine, as long as there's, a adiabatic process, an isothermal process, and an isovolumetric process. Doesn't matter whether you call it A, B, or C. And we might as well put here net also. Oh, well, I guess we have to, because it says fill in the chart, and it's got a net in here. Okay. Now, I would encourage you, the same in class, and so let me just remind you here on the exam, start with the ones that are zeros. Then go to the state functions, and then go to the non-state functions. All right, so let me start with the zero ones. When is the change of internal energy zero? Well, that's if the molecules don't go faster or slower, and that's the isothermal process. That would be the B to C in my case. So where it keeps the same temperature is a delta E of 0. Now, I suppose, since it's a state function, we need to remember that in a full cycle, it adds up to 0. So I'm going to put a 0 there too, which is kind of helpful, because if I get one of these, I also got the other. Now, when is the Q 0? Well, that's again during an adiabatic process, meaning we either did it so quickly that it doesn't have time for heat to change, or it is so well insulated that we don't let heat flow in and out. But that was the description from A to B. And then, of course, when is the work equal to 0? Well, work is that force times distance, and so if you don't have any distance, you don't have any work, and so that would be things where the volume doesn't change, the isovolumetric. So I would do this problem the following way and start right there. Okay, so I've done all the ones that are zeros, okay? So now I would fill this in by saying, well, which are the state functions? And this is the state function. And so as we say here, the delta E is NCV delta T. And this is just like the problem, I guess it was 2B, where we said, hey, this equation was derived for constant volume, but in this problem, we only have constant volume from C to A. Can I use it for the other ones? Yes, because it's a state function. So I would encourage you to use this column. In fact, it's going to be kind of easy because it's got to add to 0, so we don't have to do it one time. and then the other one is going to be equal and opposite. Of course, I do need to know the CV, and I need to know the delta T. And the number of moles is given, so that's pretty easy. So 1.45 for the number of moles. The CV we get from the number of degrees of freedom. So let me remind you that it did say nitrogen, and so nitrogen has those 5 degrees of freedom we talked about. It can move x-axis, can move y-axis, and z. So there's 3 degrees of freedom. And then it can spin. See if I have something that looks like a dumbbell. This might be the closest thing I have handy. It looks like a dumbbell, so maybe a nitrogen atom on this side and a nitrogen atom on this side. And so it can rotate around from the camera. I guess I'd call that a z-axis. But it can also rotate this, which I might call it a y-axis. But this rotation is so small and negligible because it's more of a inline, and the moment of inertia is so small. Remember, all the mass is at the nucleus, not even out at the electrons of the atom. This doesn't carry any energy. So there's only 5 places where the energy can go. There's only 5 degrees of freedom here. So this becomes 5 over 2R for the molar specific heat for this gas, the nitrogen. It's a diatomic molecule. Now I need to do the change in temperature. So why don't I just go from A to B? So this would be the temperature at B, 373, minus the temperature at A. And I don't quite have the temperature at A. I also don't have the pressure at A. So there's 2 things I don't know. And I point that out because I was first thinking, oh, I'll just do PV equals nRT, but that only, can find temperature if I know pressure, volume, and number of moles. And sadly, I don't know pressure. So there's 2 things I don't know. So I won't try to solve it that way, but I will remind myself that the A and the B are connected through the adiabatic process. And the adiabatic process says the pressure at A times the volume at A to a power of gamma would equal the pressure at B times the volume at B raised to a power of gamma. And so maybe that's the approach. And if I did that and found the pressure, then I could use this and get the temperature. But I could also just plug this into here and replace pressure with volume over nRT and reduce this to temperature at A times volume at A gamma minus 1 is equal to temperature at B times the volume at B gamma minus 1. And that's what I'll go ahead and do because I'm looking for this temperature at A. So I don't know that number. I don't know the temperature at A. But I do know the volume at A, and that is 33 liters. And I also know the gamma factor because this is the ratio of the molar specific heats. And again, CV is the 5 degrees of freedom, and CP would be 1 more R greater, so would be 7/2, and that all comes out to be 1.4. And I think we mentioned that back in problem number 2, where we were asked to find out, is this monatomic or diatomic? And number 2, we found out it was monatomic, but had that ratio come out to be 1.4, we would have said it was diatomic. And so that's what we kind of showed back there in number 2, that the gamma for a diatomic is 1.4. Okay, so if I take 1.4 and subtract 1, this is then just raised to a power of 0.4. And then the temperature at B, since it was the boiling water, is 373. And the volume was given as 6, so 6 and then raised to a power of 0.4. And this will allow me then to get that temperature at A that I need to fill in this chart. So I'm going to take this 6 and divide it by that 33. Imagine moving it over here and then raising that to a 0.4, and then multiplying that by 373, and coming up with a temperature of 188.6 Kelvin. Okay? So there's my temperature at A, and that's the number I needed up here, 188.6 here. All right, so if I now calculate this, 373 minus that last answer, so there's the change in temperature, just working backwards, times R, times 5 over 2, times 1.45, I get 5,554 joules during the process to A to B. And that kind of makes sense. From A to B, we are doing work on it. We are squeezing it because there's no Q, and that goes up by that much. Which, remember, the first law of thermodynamics says these two have to add up to that one. So this would be 5,554 also. And so that was the kind of nice thing, is I don't have to do these non-state functions. Usually they're harder ones because I got to the state functions. And of course, remember, a state function, it's got to go through a whole cycle to come out to be 0. So without bothering to sit down and do another calculation, I know this is 5,554, but negative as it goes from C to A. So it's cooling down. And again, the first law of thermodynamics says these two have to add up to that 1. So we must have taken out the 5,554 joules from C to A while, we cooled it down and didn't do any work. And so these two come out to be the same negative number of the energy coming out. All right, so now we need to look at kind of our last piece, where these two apparently have to be equal and opposite because they got to add up to 0. And the B to the C is the isotherm. And maybe the way to do the isotherm is to focus on the work, which is negative the integral of P dV, because that's the one where you can factor, the pressure doesn't stay the same, but when you replace it with nRT over V dV and calling it an isotherm, meaning the temperature stays the same, the stuff in the numerator we can factor out, and then when we do the integral of dV over V, we get a natural log of final volume over initial volume. And so let me go ahead and just calculate the work. And I think we have these numbers. I'll put the negative here, and then the number of moles. Let's see, number of moles was at that 1.45, R 8.31. The temperature is the boiling water temperature, 373. And then the natural log of the final volume. So as we go from B to C, the final volume is 33 liters over 6 liters. And so this would be then a negative 7,661. Again, well, maybe I should round it to a 2. But again, notice the negative, meaning, of course, the gas expanded. It was losing energy as it did work on the environment. It had negative work. So this is a negative 7,662, which means, of course, this is a positive 7,662. And then to finish this, you can see that these would be, again, equal and opposite. If we take the 7,662 and subtract the 5,554, the full cycle, 2,108 joules of heat go in, and 2,108 joules of energy in the form of work come out. That's why the total change of energy is 0 once we complete the whole cycle. And so that's why this is referred to as a heat engine, is we put heat energy in and we got work out. The total change is 0. The engine's gone through the whole cycle and it's ready to start again and do some kind of work, run a car or something, make a car move, or a lawnmower or something along those lines. Anyways, but that's the answer. And you can stop there. You don't have to ever really find the pressures here on the side of, what's the pressure at A, what's the pressure at C, or what's the pressure at B. But certainly at this point we could, since pressure would be nRT over V. And so we could fairly easy find these pressures, and some of you may have done it that way and found pressures and used that in order to get some of these. So there's a lot of ways of getting there. Maybe I better move on, and I'm kind of tempted to get the pressures, but again, definitely in an exam, I wouldn't bother to solve and take the time for everything if they're not asking for it. All right, good. So we're a hour 15 into this, which I guess technically would be halfway through the exam. And I'm at a good pace, if you will. Hopefully you'd be even a little ahead of this pace. You wouldn't be chit-chatting away like I am here. Okay, so last problem, number 5, if I can find it. Aha, here it is. It says, the figure shows a cycle with 1 mole and monoatomic, ideal gas. And it's taken through this process. All right, maybe we should talk about this process because it's a PV diagram where they give me the volumes in liters and they give me the pressure in atmospheres. I want to be careful there because I like the pascals, so things come out in joules. And they tell me this process, the A to B, is an isotherm. And it asks then, what is the efficiency of this cycle? And the other part here then asks for what is the efficiency of the Carnot cycle operating between these same two temperatures. So it's a two-part question. It's the Carnot cycle is the idea of what could be the efficiency of this engine based on the temperature if we went through a Carnot cycle. This is clearly not a Carnot cycle. Remember, the Carnot cycle had 2 adiabatic and 2 isotherms. This one has an isobaric, isobolometric, and isotherm. So this one's got to be at least something less than the Carnot cycle. So the Carnot cycle is a good one to say, what could we do? Because we know we can't be 100%. But part A is what actually is this efficiency. Okay, well, maybe I'll do B first. Because if you remember B, the Carnot cycle, we worked out that it would be a little equation based on temperatures like this. It would be 1 minus the temperature of the lowest temperature, the cold temperature, divided by the highest temperature. And as I'm looking at this diagram here, they've given me pressures, they've given me volume, they've given me the number of moles, and it's then the temperature that I can easily find, because temperature then would be pressure times volume divided by nR. So I'm going to just take that advantage and say, well, what is the temperature at each of these locations? And so let me start with A. So the pressure in pascals would be 5 times 101,300 pascals for each atmosphere. Okay, so there is the pressure, 506,500 pascals. The volume, of course they write in 10, but they mean 10 liters, in cubic meters would be 0.01. So there's P times V. And then I divide it by n, which is just 1, so let me not mess with that. Let me divide by r, 8.31. We're looking at a temperature at A at 609.5 Kelvin. And I'm thinking that's going to be the high temperature. Because this isotherm, it stays the same temperature. So the temperature at B is still 609.5 Kelvin. And then, of course, to lower the volume by a factor of 5, but to keep the pressure the same, really means we've got to cut down the temperature by a factor of 5. So if I divide by a factor of 5, I get a temperature at C of 121.9 Kelvin. Now, maybe I should just confirm that because I did just the proportions here. Let me just do this again. Let's take the pressure at C, so that's 101,300 because it's 1 atmosphere. Let me take the volume, 0.01, that's in cubic meters. Let me divide it by the number of moles, that's 1. Let me divide it by 8.31, and do I get, 121.9. So these are my 3 temperatures. So I've got the temperature, the pressure, and the volume everywhere, and that's actually going to make this probably a fairly straightforward problem here, or at least B is, because I can then just go 1, and the coldest temperature then is 121.9, and the highest temperature is 609.5, and so if I go 1 minus 121.9 over 609.5, I get 80%, so 0.8. All right. So this is actually a pretty good difference in temperature. Well, factor of 5, that's where it is. It's 1 minus 1/5. That's 80%. So it's that factor of 5 that gives me the potential of having a pretty efficient engine here, an 80% efficiency. Again, notice it's not 100%. And so the question really is, if you actually built an engine under this cycle, you say, okay, what is the efficiency of this engine? It's going to be less than 80%, and so how much less, you might be happy or unhappy with this particular cycle. If it's way under, which I know this cycle, so I know it's way under, you're going to say this is a terrible operation. And it's an isotherm, which takes a long time. So this cycle has no practical uses. Isotherms are so slow, it's not going to make a good engine. And this particular one with an isotherm is so inefficient compared to the isotherm of a Carnot engine. It's like, why would you ever build an engine this way? You wouldn't. If you're going to do an isotherm, you might as well do it with efficiency if it's going to be slow. But anyways, that's just a test problem here. So let's actually find the efficiency of this engine. Now, if you remember, the definition of efficiency is the work done. So we can look at this and say, what is the work done in this cycle? Divided by how much energy is put in to this. And so maybe we ought to make a chart like we just did in number 4, an A to B, a B to C, and a C back to A. Maybe even a net down here. And say, okay, what is the change in internal energies? What is the heat added or taken away? And what is the work done to or by the gas? Okay. And so up here in the numerator, this is the net work. And so it's that number there. Divided by how much energy you put in. And this you've got to be careful with. So it's not the net heat. This is how much you put in. And if you come back to this cycle, you can kind of see that when we go from A to B during this isotherm, kind of like number 4 back here, during the isotherm, the B to C, there is thermal energy going in. Of course, there's work coming out in the same amount. That's why the temperature doesn't change. The change in internal energy is 0. But we are going to have some thermal energy going into our engine from A to B. And so A to B is going to have a positive number. And that's part of this number here. Because if you look at C to A is an isovolumetric. And we got to be adding energy into it. And this number here then will become the sum of those two. And that's probably the hard part of this particular calculation, is to realize it's all the heat energy. And so anything that is positive. Now, B to C is negative, so that would not fit with our heat going in. But this number here is really the sum of the two H's going in. It's not just one of them. And like I said, that could easily get overlooked. In fact, I'm going to probably make this calculation, I think, a little easier on myself and say, remember the work then is the difference, according to the first law of thermodynamics, of how much did you put in heat-wise and how much did you get out. That difference, and the reason there is a difference because of the first law of thermodynamics, is the work. And I say that because then this reduces to 1 minus the heat going in, coming out, divided by all the heats going in. And I just said that the heat coming out is that term. It's going to be a negative. And the heat going in is going to be the sum of these two terms. So what I'm kind of telling myself here is if I could just get this column, I don't need to do this column and get the network, although it should come out to be the same as this one, so I could do it either way. But I'm just going to focus my attention on heat energies here. And maybe I don't have to fill in this whole table. Maybe I can just focus on these. Although I might as well do the zero ones. The zeros are the easy ones. And that was my comment back in number 4, that you might as well do the zeros first. So the delta E is 0 during an isotherm. So I might as well put a 0 there. And the net cycle is 0, so I might as well put a 0 there. The Q0 during adiabatic, we don't have any of that here. The work is 0 during the isovolumetric, and that would be the C to the A. Okay. All right. But what's really neat about this, I think, is we don't even really need to do all of that. The A to B, as we mentioned back in number 4. No, 4? Yeah. The isotherm, so in number 4 it was here, we had the Q and the W equaling the same thing. And we did this calculation for the work. And then the Q would be the negative of that. So I'm just going to say the Q from the A to the B then must just simply be nRT, natural log of final volume over initial volume. And so that's going to go right here. And the other two are pretty easy because the Q from the B to the C is isobaric. So it would be NCP delta T. And the Q from the the C to the A is isovolumetric, so it would be NCV delta T. So I can just focus on these 3 Qs. I don't need the net. I don't even need these zeros. I just filled them in because I said that's kind of my first goal, is just to do those. And actually, if I followed that pattern, I'd do a lot of extra work because I would do the delta E's first because it's a state function. And then I wouldn't do these Q's and W's until the end. But now that I see what I'm after, I'm really just after the Q's. And fortunately, the Q's here are pretty easy to get based upon temperature. And that's what I've already done, is got their temperature. So I can just go ahead and start plugging some numbers in here to my calculator. So let's do the A to B. So it would be the number of moles, which is 1, times the R, 8.31, times the temperature during this isotherm process, which we said was the 609.5, then times the natural log of the big volume compared to the little volume. Well, the big volume is 50 and the little volume is 10, so that's a ratio of 5. So that would say 8,152 joules plus must go in during this isotherm, which, by the way, the work then would be a negative 8,191 since these two have to add up to 0. But again, let me not even just fill in these other ones. All right, now the B to C being a constant pressure, again, I'll just do the same calculation. It'll be the number of moles, 1, times CP. Well, here's where that comment, what kind of gas is it? So it's monoatomic, so it has 3 degrees of freedom. So CV would be 3/2, and CP would be 5/2 R. So this would be 5/2, so 5 over 2 times R. Okay, so there's the CP. And then times the change in temperature. So it would be the temperature at C, 121.9, minus the temperature at B, 609.5. And I would then get a negative 10,130. So as we go from B to C, we got to take some thermal energy out. And of course, we're also squeezing it, so this would be a positive number here. So we're taking a lot of thermal energy out, but we're also squeezing it, so the change of internal energy is not as great as the heat we took out because we squeezed it. But again, I'm not even going to mess with that. Because in the last one, the CV would be the isovolumetric process, the C to the A. And so again, grabbing a calculator here, I'm going to go 1 times, and CV, again, remember it's monoatomic, so it would be 3 over 2 times R, 8.31, times the change in temperature. And the final temperature is 609.5 at point A, and the initial temperature is 121.9. And I get, for this one, 6,078 joules go in. All right, so now I can come back up here and begin to finish this. So remember, the Q is the energy that comes out. That's the negative number, so that's the 10,130. That's the only thing that comes out. But again, I'll repeat that the hard one here might be making sure you add these two together, because this is the heat that goes in, and it goes in twice, okay? So the 8 and the 6 make a 14. 1, is that a 230, I believe? Let's see, that carries over 1230, yeah. So that's 230 there. So the efficiency now becomes, let's see, 1 minus 10,130 over 14,230, and 28.8%. So I told you it was a really terrible efficiency. So we could get as much as 80%. We are only getting, I'll call it 30%. So we've kind of missed all that. All right, well, I hope that helped. I hope if you saw any thing that you did wrong, or maybe a way to do it better, because there are many ways of doing this, and hopefully you got some idea of what your grade is, because this is obviously a big test, a long test, and there's lots of you, so it takes me quite a while to get all these graded, but I will do my best working all weekend to get these complete so you can have your scores. All right. Best of luck.